We are group 6 and today we'll be talking about the evaluation of a data structure. Have you ever tried Googling something and getting suggestions to complete your search? Well, this autocomplete function can be done by a trie, the data structure we have chosen for our project. Trie is a tree-like structure that stores and retrieves words. Each node in the trie represents a single character, and words are formed by following paths from the node to the terminal node.
These are the questions that we asked the chatbot, mainly about its key characteristics, practical applications, advantages and disadvantages, and time and space complexity. For key characteristics, it establishes the foundation mechanic of tries. Why does it matter? Without understanding the core structure, like nodes, edges, hierarchical organization, and properties, we cannot grasp how tries work. The question asked around its key characteristics also explain why tries are uniquely suited for string operations. For practical application, it links theory to real-world utility. So tries is able to be implemented into things like autocomplete, spell checking, and network routing. For advantages and disadvantages, it highlights when to choose tries over alternatives. So it reviews things like speed, space efficiency, weaknesses of memory overhead. And finally, for time and space complexity, it quantifies efficiency for informed design choices, like when is the best case for different scenarios.
Now let's talk about the key properties of trie. Firstly, trie stores words character by character, making prefix-based searching highly efficient. Secondly, words with common prefixes are stored together. This helps with optimizing space usage. Thirdly, each node contains a Boolean flag marking, indicating where a valid word ends. Here is a visual representation of how trie works. Using the words cat, car, cut, dog, and do. For cat, we start at the root. We create nodes for C, A, and T, and we mark the node for T as the end of the word. For car, we reuse the nodes for C and A. We add a node for R and mark it as the end. For card, we reuse the path C, A, and R, and we add a node T, and we mark it as the end. For dog, from the root, we add nodes for D, O, and G, and mark G as the end. For do, we reuse D and O from dog, and mark O as the end. The real-life applications for trie are autocomplete and spelling correction.
Now we explain the time complexity of trie operations. In the trie, most operations like insertion, search, and deletion run in OM time, where M is the length of the word. This is because we only need to traverse each character one by one, no sorting or hashing required. For example, inserting car goes from the root CAR, so the time taken depends on the length of the word, not the number of words in the trie. Next is space complexity. In the best case, where many words share common premises, try and use space efficiently. This gives us ON, where n is the number of words. In the average case, or worst case, where all words are completely different, try has to store every character individually, leading to ON times n, where m is being the maximum word length. And lastly, in the average case, some words share prefixes, others don't, so space becomes ON times k, where k is the average word length. This visual shows how space usage changes in different cases. On the left, words like car and cut reuse most of the path, that's the best case. In the middle, there's partial reuse like cat and can. And on the right, each word takes a separate path using the most space.
The trie data structure has several advantages, one of which is its fast prefix-based searching. For example, you are searching for the word cat, C-A-T. Trie only requires traversing 3 nodes, from C to A to T. Whereas compared to binary search trees, which may take multiple comparisons depending on tree depth. Another of its advantages is that it has no hash collisions, as it does not rely on hashing functions. There are also some disadvantages of using try compared to other data structures. Try has a higher memory usage than other data structures as try stores each character of a word in a separate node, leading to high memory consumption. So compared to hash tables, which store entire words as keys, try requires multiple nodes for a single word. Try is also inefficient for short and unstructured data such as storing user IDs like AB129X. Try also has slower lookups than hash tables in exact word matching.
So here are some insights on the responses from ChatGPT. It is accurate and it gives factually correct information and uses reliable sources or logical reasoning. It is complete and fully covers the question asked and includes necessary background information. It is very relevant and it directly answers the question and it avoids unnecessary or off-topic information. And it is clear and simple in its language use and it has a good structure and display to provide information. And here is a demonstration of our code.
Hi, today I'll be going through the chatbot that we created using Python. It makes use of the try data structure to perform operations like autocomplete and spelling correction. Let's start it. We'll start off with autocomplete. For autocomplete, it gives suggestions to words that are incomplete. So if I were to put example PLA, it would suggest words like play or player that are completed words. For spelling correction, it detects the misspelling and implements the closest match. So if I were to misspell play, it will automatically implement the word play. But what if the word I typed was neither incomplete or incorrect? Our chatbot offers the user to add the word into its dictionary. So for example, playing is a correct word, but it recognizes it as wrong as the word playing does not exist in the dictionary. So in order to add playing, you can add playing into its dictionary, and now it will be recognized as the correct word. Every word that a chatbot knows comes from a file called dictionary. This ensures that it remembers everything that it learns across sessions. Finally, to exit, we just simply give the command exit. This is how try can be used in a real-world setting like Google or other search engines. Thank you.
So we have come to the end of our presentation. Overall, the project deepened our understanding of try and its performance across different contexts. It also shows the potential that AI have to support learning and development in computer science. And in the future, there is a possibility of work expansion using chatbots and integrating other data structures or exploring more advanced AI models like Claude or Google Gemini to broaden the evaluation landscape.